Okay, so this is, again, so like I said, group theory is completely different from all the calculus that we've done before. We don't want to treat it like trivia, like a little game where we just figure out what this molecule is, but we want to actually use it to apply it to spectroscopy. Now that takes a little bit of time. So this first exam that we're going to have is just going to be the trivial part. Like I give you water and you say, okay, that's a C2V molecule, or I give you ammonia and you do the little flow chart, which I've got here, which we'll pass out and you can practice with, and you see C3V or ethane where it's not eclipsed, where it's gauche. Then you look at it and you see that it's D3D. If it's eclipsed, it's D3H and those kinds of things. So really getting proficient with the flow chart and getting proficient in identifying the point group of the molecules, and then also your Lewis dot structures. So the angle between the hydrogens, since oxygen has 4 electron domains around it, that oxygen should be an sp3 hybridized set of orbitals around the oxygen. So we'll say that those hydrogens are 109.5 away from each other. Okay, that's a good first guess. It's not exactly accurate, but it's close enough at this point that that's what I would be looking for on the exam. So multiple choice, you just got to be good with that and identifying those things. Now there's more to group theory, but that's all we're going to focus on for the first exam. Okay, so let's jump into it. So last time we talked about the symmetry elements, and we're going to practice that this morning. But once we get those symmetry elements down, and again, we're going to look at those on the Otterbein side. Then we have certain groups of symmetry elements that will define that molecule. And so these groups of symmetry elements, that's what we mean by group theory. So it's operations that this molecule has that leave it unchanged, and it's capturing the symmetry of the molecule. And then once we have that, there's been a notation derived for all of those different groups, and it's called the Schoenflies notation. So there's several things that I will refer to in this group theory section that if you don't know the vocabulary words, you're just not going to understand what I'm talking about. So Schoenflies notation is the group theory designation, like C3V, C2V, TD, and so on. Later, we're going to have Millikan notation, and it's a totally different thing. So you need to know the difference between a Schoenflies notation and Millikan notation and all of that. So they're just named after the scientists that were important in those fields. Okay, so this is, when I talk about the Schoenflies notation, it's a kind of a strange word. Don't just blank, say, oh, that's the point group designation. But I want to use the technical term so that you know those technical terms. So let's practice on the symmetry elements, which we didn't get to finish last time, okay? And then we'll get into assigning the point group. Okay. So we'll practice. Uh-oh. Okay. Bear with me while I get the video switched over. Let's see. Let's just do this. Yeah. There it is. Okay. Okay, fantastic. So let's do the symmetry tutorial first, because that's going to go through all of the symmetry elements. And we started a couple of those last time. Let's see, I just don't see the mouse on here. Okay, I'm going to change things again, because it's just going to make it a lot easier for me. Let's go to display capture. And do duplicate. Okay, don't freak out. It's going to be trippy here for a second. Okay, and display capture. Yeah, there we go. Isn't that cool? Right. Yeah, there we are. Okay, that's what I want. So that's going to be great on the video. All right, so here we are. We're going to do the tutorial first up here in the upper left, and then we're going to do the gallery, and we'll pick a few molecules and look at their symmetry elements and see how what we're talking about. But we'll get some of the gallery in the tutorial, and then we're going to do the symmetry challenge, okay? And the symmetry challenge is what you want to work through with the flow chart. So when we get to that point, I'll pass out the flow charts and then we'll be ready to go. Okay, so let's go to the symmetry tutorial. That's weird. Okay, let's try this. Yeah, all right. So we did reflection planes. Let's just do one real quick one. The reflection plane, you know, this is ammonia. This is typically how you draw it, with a straight bond here, and then the wedge coming out in front and the dash going in the back. Can everybody look at that and see the wedges and the dashes? And so we have the 3 reflection planes. I can turn them all on. They all have the NH bonds in them. Okay, so there's 3 reflection planes. It looks like 6, but it's really 3. You see at the top, we've just taken those 3 planes and it's divided the molecule into 6 parts. Okay, so if we reflect through one, that's that reflection plane, that's that reflection plane, that's that reflection plane. You'll see the reflection planes. Okay, I can turn them all off and I can pick one, and you can see if we reflect in that plane, it's just the left and right side of the molecule reflecting into each other. So that's the reflection plane. You can do this for water as well. So here we have that one. So when we draw water, let's say we draw it like this on our board or on our screen. You know, in terms of the lab, I'm testing you on your coordinate system too. No, you can't see this on the video. I'm sorry. So this is Z, because that's the symmetry axis, that's the rotation axis. So Z is up and down, okay? And then we have this right-hand rule, which essentially is counterclockwise X, Y, Z. X, Y, Z. So the right-hand rule is from vector calculus. We use it in physics, we use it in chemistry. And so that would be the Z-axis is your thumb, okay? And if you're doing a cross product, you have X cross Y gives you Z, and it's the right-hand rule. Do you see that on the board now? See, X cross Y gives Z, so X, Y, Z, that's the right-hand rule. Now, is there anything magic about right hands? No, it's just that's the way the character tables were made. And so early on in physics, they just chose a right-handed coordinate system. It's different than a left-handed coordinate system. You see, they're mirror images, but they're not superimposable. Okay, so that's the right-hand coordinate system is how the character tables were made. So we need to make sure we label things the same way as the character tables, so that we're talking the same language. Okay, so that means the up axis is Z, coming out is X, and that way is Y on the water molecule. Why is it important? Well, look here. This is the reflection in the XZ plane. So X is coming out, Z is up, so that should be this plane right here. And so if we play that, yes, that's the reflection in the XZ plane. And then the other one, you can't tell because it's in the plane of the paper. It's just the front half of the atom reflecting into the back half of the atom. So all planar molecules have at least one reflection plane, the plane of the molecule. You just can't see anything happen. So if I play this one, you see nothing, you can't tell. It's just the front of the ball moving to the back of the ball, and you can't see anything. Yeah, so it's splitting the molecule in half. Even if I were to turn it sideways, you wouldn't be able to see anything happen. Yeah, this is that plane, and this is the XZ plane. We're standing on the XZ plane right now. Okay, and we can see that reflection. Yes.
Actually crossing each other, just like
it's just trying to show you what you should think of visually. It's like looking to both sides, like if they reflect in. So there really isn't any motion associated with it, but that's a good question. So they're just animating it to kind of show that it's the action of reflection. They're reflecting to the other side. Yeah. Then we do inversion. So this one, I think it's best when we talk about something like benzene, where you can see that there's no, that there's nothing in the middle. You can see if we display the inversion point, it's always a point of inversion, or an inversion center. It has to be the center of the molecule. It has to be the center of mass. In fact, the point, when we say point group, we explain group. Group is the group of symmetry elements. What's the point? The point is the center of mass of the molecule. So it's the symmetry around that point That makes it a point group. Okay. There are space groups. So in crystals, you have spaces. You have sort of infinite lattices. And so there's a whole bunch more symmetry you can have in a crystal lattice that you can't have on a molecule. Like in a crystal lattice, you can have a repeating pattern where it goes one step and up and then one step and down, and those are reflections. So it's a slip and a reflect and a slip and a reflect. So we can't do that in a point group because the molecule is at a single point. But if you have multiple points in a space, then you have other symmetry things that can happen. So we're not going to get into space groups. That's in advanced inorganic. You might get into some of that. Okay, but this is a point group. So let's animate this one. So everything's going through the center of mass to the other side of the molecule. Now, what if I took this and I changed this atom to a fluorine? Like in your lab, I think you have fluorobenzene. I break the symmetry because this fluorine doesn't have a fluorine on the other end that it can invert into. So it's no longer D6H, it's C2V, how did I know that? Well, you go through the flow chart, okay? But if like water, the left and right side, remember this is now a fluorine, okay? The left and right side look the same, meaning there's a reflection plane this way. It's planar, so the front and the back look the same, and it has a C2 rotation axis. That's it. So if I put a fluorine here, this molecule now looks like water from a symmetry perspective. So it'd be C2V. And that's what you'll want to get to as we get past this first exam and you use group theory more frequently. You should have classic examples of each of these molecules in your head. Like water is C2V. And if you can look at the molecule and say, that looks like water from a symmetry perspective, then I know it's C2V. Or if something is threefold symmetry like ammonia, and you look at chloroform. Chloroform has 3 chlorines on the bottom and a carbon-hydrogen axis. Has the same symmetry as ammonia. So if you know ammonia is C3V, chloroform is C3V. So you start to see the symmetry in the molecules. And that's a faster way to do it. And actually, that's where I want you to get to. I don't want you to be chained to the flow chart. Any questions on the inversion axis? Let me just show you one more quick one, ethane. So we're going to look at this molecule. That's how I would draw it with the wedges and dashes here. And the wedges and dashes here. Notice to draw it as this staggered formation, the wedges and dashes are on the opposite side of the molecule. And here's the inversion center of mass of the molecule. And then I play it, everything goes to the center of mass to the other side. So this hydrogen here is paired with that one under inversion. See that? And this hydrogen in front is paired with the one in the back. So it's straight through the center mass of the molecule. You look to the other side, is there a hydrogen there? If so, then it's possible it has an inversion center. You see a hydrogen here, straight through the center mass of the molecule, is there a hydrogen there? Yes. Okay. Here's a carbon, straight through the molecule, the center mass, is there a carbon on the other side? Yes. So you've now said, okay, that's got an inversion center. Every atom has to have a pair through the middle of the molecule to the other side. Okay. If I had just a single fluorine here, then that would break the inversion because there's not a fluorine over there. Okay. Everything else, but it has to be every atom. It can't be a single atom off. That's going to break the symmetry. Okay, let's go to proper rotation. Since we had ethane, let's go back to it. Okay. First of all, can you look at that molecule and see any rotation axes? I mean, you see that it has C3s and C2s, but like, do you see them? Where do you see them? Yeah, how many rotations, or like what fraction of a full rotation would you have for the molecule to be unchanged? Like, divide the circle into how many pieces? 3. Yeah, you see the 3 hydrogens? So you're going to take the circle that it could rotate and divide it by 3. So then you're just moving the hydrogen a third of a turn and it finds another hydrogen. Like what fraction of the full circle do I have to go to hit the next hydrogen? And it's a third. Okay, so that's the C3. Yes, that's what the 3 stands for. Ah, yes. Um, the C and the D. Yes, so these, a good question. So at this point, we're just looking at symmetry elements. So it's just these five over here, identity, reflection, inversion, and so on. The capital C's are always rotation axes, okay? There's also a capital C in the Schoenflies notation of the point group. Those are two different things. So in this case, we're talking just about the symmetry elements of a rotation. So in this case, C3, there is no D rotation axis, to answer your question. There is a D Schoenflies notation point group. So that's a point group. So that's in the box of point groups. This is just this rotation axis. So all the rotation axes, the proper, you see, proper rotation, those are all C. And so you can go, again, 1/3 of a turn, 1/3 of a turn, and if we do it again, the hydrogen has come all the way back around to where it started. Okay. And then we could go in the opposite direction. That's what the -1 means, C3 -1. So we're going in the opposite direction. Okay. There are some C2s on here. So this one coming right out at your face is a C2 axis. So what I'm doing is I'm taking the full rotation of the molecule and dividing it by 2. So I go halfway around. So if I have an axis coming out of the board right there and I rotate this 180 degrees, it rotates around that axis and that hydrogen moves here and this hydrogen moves there. These are the hard ones to see on ethane. So this is, I'm starting you with like one of the more tricky ones. So here it is. There's 3 of those. See that? I got lucky. I picked the right one. So that's a C2 that's perpendicular. This is a very important phrase. It's perpendicular to the original C3. So we have a C3 axis. 3 is the biggest number of all of these. So that's the principal symmetry axis. And then we have 3 C2s that are perpendicular to that. There's this one. There's that one. It's like rotating, I don't know how to describe it, but it's 120 degrees different from this one. So this one is coming out at us. This one is like 60 degrees off the screen, and this is the other one. So those are the 3. So if I show these axes, here's the C2 that we're looking down. Here's the other one. Okay, and here's the third one. So let me pull these up. Notice if we have threefold symmetry and we find one C2, those other C2s are a third of a turn away. Yes.
So is this what it means whenever on the flow chart it asks if there are any perpendicular C2 axes?
That's why I emphasized that. I said that word perpendicular to the principal symmetry axis. So where's the principal symmetry axis? We're looking right down at right now. So if I show that one, that's the C3. So you see those 3 C2s are perpendicular to the C3. And what that does on the flow chart is that kicks us over to the D groups. You had talked about D groups. And so you see on the flow chart over on the right, there's D groups. Over on the left, there's C groups. And we'll look at that flow chart in a second. Okay. The water molecule just has one C2 axis. It's right, this one, it's pointing up and down. And this is the rotation animation. So we can look down that C2 axis and see the rotation. Okay. That's not controversial. Just spin the molecule around an axis. Okay. Yes?
Why doesn't it go backwards like the other?
It's a good question. Because those two operations are identical. Like if it goes clockwise and it goes counterclockwise, there's no difference. Okay. Whereas if we were on the ethane molecule, if we go clockwise, watch this hydrogen here. Okay. So it's now here. Okay. If I do this one, if we start at this hydrogen and I do it now, it's here. See, those are two different operations. And so they have to be unique. Whereas the water one, since there's really only 2 turns to get back, whether you went clockwise or counterclockwise, it'd be the same answer. Yeah. Whereas in this case, we have to have 2 different symmetry elements because they give you different results. And there's you ought to thank me even though you don't know. There's a lot of math behind this. When you rotate that, what are you doing to the Cartesian coordinates on all these atoms? You're changing them. And there are matrices that do that. So every one of these symmetry elements has got a matrix that you can multiply by the Cartesian coordinates on the atoms that would produce this rotation or this reflection or this inversion. And I'm not making you learn it. Yeah, that's a grad school thing. Okay, but yeah, not to scare you from grad school, but that is those matrix transformations are the math side of group theory. So be careful going around saying you know group theory or you love group theory, because you might run into a mathematician and they start talking about matrices and everything, and you're like, whoa. So you know a little bit about group theory, you won't know a lot about it. You'll know the applicability of group theory to molecular spectra, which is a good thing. Okay, let's look at improper rotation. Okay, so we'll use the same molecule. Notice, yeah, let's do this first. Let's look at this. So notice that as I'm moving this a third of a turn, when I get to a sixth of a turn, I'm right on top of that hydrogen. How could I get to that hydrogen? Right? Because these are hydrogens. I've got 3 hydrogens on top, 3 hydrogens on bottom. Could I somehow get this hydrogen a sixth of a turn and then down to that one? And that's what an improper rotation does. So that's why it's a C6. We do a sixth of a rotation and then we reflect it. So let me turn this on, and you can see that there's 2 pieces combined. There's a C6 rotation, which is 1/6 of a turn, and then a reflection. So watch, let's follow this guy in front right here. So it moves a sixth of a turn and reflects down, and now it's connected to that hydrogen. This is, if 2 hydrogens can be connected by any symmetry element, they are by definition equivalent. So that tells you something about NMR, doesn't it? We've got equivalent hydrogens. They're going to be at the same chemical shift. And so this is a way to know that every hydrogen in this molecule is going to be at the same chemical shift value. You got 6 hydrogens, but you're going to have 1 peak in the NMR. Maybe some hyperfine splitting, but you'll be 1 position in the NMR because they're chemically equivalent. Also, acid-base chemistry. Every one of these hydrogens has the same pKa because they're chemically equivalent. So if you can exchange any 2 elements using any 2 atoms using a symmetry element, then by definition they have the same chemistry. So that's a very important chemical application of group theory. So this is an improper rotation. It's nowadays they try to get away from proper and improper because it sounds like moral language. So they just call it the rotation reflection operator. So sometimes you'll see it written like that, the rotation reflection operator, which is more accurate. It does tell you rotate than reflect. But historically it was called the proper and improper rotation. Yeah. So I don't know. So that's the C6. And looking down the top, you can see how all of them rotate 1/6 of a turn and reflect through, and they come back. You know, the ones on the bottom come up and the ones on the top go down. Yes, yes, yeah, and reflections and inversions. So if you can get one atom to go to the other and they can exchange places, they're chemically the same. Yeah, it's very cool. Okay, so that's all the symmetry elements. Here's your chance for just a quick review on any one of them. You okay with reflections? Yeah, rotations. Take the circle that you could rotate and divide it into how many pieces. That's the number down at the bottom. So if you're moving a fourth of a turn, then that's a C4. If you're moving a sixth of a turn, it's a C6. Like in benzene, you have a C6. You move it 1/6 of a turn, and now your hydrogens and carbons are in the next hydrogen carbon spot. Now let's use this to come up with the Schoenflies notation for the point groups. But before we do that, I want you to write your names on this little sheet, pass it back. Very, 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 very legibly for me, please. This is for my use only, so I can learn your names. Smile. Yeah, you got those two. And I want to see all your faces. So you gotta look. Okay. Make sure you can see the camera. 1, 2, 3. Got those two. This one. Everybody looking. All right, I see you. Yeah. I'll make a little E so you can see. Thank you. I'll take your seats up. You got 2 more? Thanks. Take this half of the classroom. Can I get you to take this half of the classroom? Everybody gets one. Okay, now. So let's do the symmetry challenge now. This is the flowchart challenge. Thanks. Thank you. So let's pick a molecule. Let's pick something easy first. Let's do ammonia. Okay, thank you. So typically when you draw ammonia, you probably draw it sideways like this, where you've got wedges and dashes over here on the left, and then you got the NH bond in the plane of the paper on the right. And so what we're going to have is we're going to have this Q&A here. The flow chart is built into this website. So that's fantastic. But you can follow along here. So the diamonds are questions or decision points, and then the little ovals are your endpoints. And you can see we go through this flow diagram until we get to an endpoint, and that's the Schoenflies notation. So the very first question is the molecule linear? Now that was my interpretation of this first question. This is the way they used to have it, but it says, does the molecule have an infinite rotation axis? So think of a linear molecule. There's nothing off of the outside axis. So I could divide that circle into an infinite number of degrees, right? And so that would be a C infinity axis if I have a linear molecule. So this first question is just asking, is it a linear molecule? And I'm not asking, is it mostly linear? Like it's really long, but it's got something on the end that sticks up and down. That's not linear. So it has to be a linear molecule. And so this is saying, does it have an infinite rotation axis? The answer is no. That we're looking at this molecule. Okay. Does it contain 2 or more unique C3 axes? So look at that next question. Notice that decision point, if we were to say yes there, look where it sends us. It sends us over here to these highly symmetric groups, these highly symmetric point groups, which most commonly will be tetrahedral. So down there at the bottom, kind of in the middle of the page, TD, that's a very common one. And another one is octahedral. It's over here. It's the middle one on the far right, octahedral. Those are the most common ones the chemists come across. Because octahedral complexes, think of a cation in water. A cation has 6 waters around it, and that forms an octahedral complex. So all of those metal with chelates around it and so on is an octahedral. So we have lots of examples of octahedral complexes. This is not octahedral, okay? And it only has one C3 axis. It doesn't have multiple. So we're not getting pulled over into this part of the flow chart. So we say no to that because it's not that symmetric. So we're going to say no. It does not have 2 or more unique C3s. So if there are any present, is there any rotation axis in this molecule? Yes, if we look right down, there's a C3 axis here. You can see that you can turn it 1/3 of a turn and you get the H's on top of each other. So we say yes. So it says select the highest order proper rotation axis, CN, if there are any present. So we can come in here and we can say is a C3. So you pick order 3 in here and hit select. Okay. So we've selected that sort of mentally, and we are, yeah, does the molecule contain a proper rotation axis? We said yes, a C3, and now we're at this one here. It says identify the highest order CN. That's why it's saying select that highest order CN. And it says, are there 3 C2 axes perpendicular to the highest order axis? And no. A C2 axis, let's see if I can do it in this deal. A C2 axis, let's see. No. Oh dear, no. Shoot, what have I done? How do I reset it? Oh no. I got a Z clipping plane here. Oh gosh. I'm gonna have to start over. Never mind. We'll just bail and I'll start over. Oh no.
Maybe refresh the page.
Yeah, maybe so. I was trying the different rotation things. I was trying to get a. Oh gosh. Okay, let's try it. Yeah, thanks. Good suggestion. Whenever. Okay, here we go. Let me quickly go through. No C infinity. No multiple ones. C3. Okay, select. Are there 2 C2s? I was trying to rotate the molecule 180 degrees, and then you'd see the hydrogens are pointing up, not down. And since you can tell that that's not the same, it doesn't have a C2. So like you can rotate it C2, but if the hydrogens don't hit other hydrogens, then it's not there. Okay, so we would say no. A C2, like if it's coming out of the plane of the board, then if you rotated it around, now it's pointing up. Yeah, and there's no hydrogens up there. Like before you start, if like in ethane, there were hydrogens up here. So we rotated it up and everybody was happy. But with an ammonia, it's just one end. You rotate it up, there's nothing up there. Yeah. Another way to think about it is look at the molecule, close your eyes, operate on it, open your eyes. If you can tell something's happened, this doesn't have that symmetry operation. If you've got a ethane, close your eyes, you rotate at 180 degrees, open your eyes, you can't tell anything's happened. That's how you know it has that symmetry element. Yeah. So it says leaves the molecule unchanged. Another way to think about that is you close your eyes, you do the thing, you open your eyes, I can't tell, anything's happened, the molecule is unchanged. You see what I mean? Everything has to go to a corresponding atom. For a C2. So it's perpendicular C2s, yes. The electron pairs and the molecular orbitals and all of those things will follow the symmetry of the atoms. So we don't have to worry about that. Yeah, so like on water, wherever the electron pairs are, they will reflect just like the atoms do. So that's a great question. What about the electron cloud? It's going to be where it is because of the nuclei. So that's a beautiful thing. So we would say no, there are no perpendicular C2 axes. Now we get over here, we're down in the middle part here, okay? And it says, does the molecule contain a horizontal reflection plane? Now, the principal symmetry axis, in this case it's a C3 axis, we've put it up and down. And when you put the principal symmetry axis up and down, then the horizontal, the sigma H is horizontal. It is always perpendicular to the principal symmetry axis. Okay, and so we're looking at this molecule. There is no reflection plane that's horizontal, because that would reflect the hydrogens up, and there are no hydrogens up. Okay, so the answer to that one's no. Okay. Then it says, does the molecule contain 3 vertical planes? So those contain the symmetry axis. Okay, so the vertical planes are vertical with the symmetry axis. So that's why it's important to know that there is a symmetry axis, the C3. We put that up and down, that's the Z axis. And now does it have any reflection planes that come out that contain that axis? And yes, this has 3. So they're like the plane of the paper that I have it up here, or the board, that front hydrogen and the back hydrogen reflect into each other. Okay, and then every NH bond is in the reflection plane. So then the other 2 hydrogens reflect, and we showed that in the animation. So we would say yes, it contains 3 vertical planes, and so we've arrived that the point group is C3V. Now this is nice. It hasn't told us if we're right or wrong. So you go through the flow chart, you think it's C3V, you can say check answers. And it tells us, yay, you got them all right. Correct, 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 correct. Isn't that fun? I mean, this is great. This is your tax dollars at work. Years ago, the NSF funded this university, Otterbein University, to build this site to teach chemical applications of group theory. I think they did a fantastic job. And so, yay for them. And yay for us, for our tax dollars. Okay, so you can get here, you can say show, and there's the axis, and play, and it'll rotate. So you can go through here and you can learn it this way. Here's your 3 planes, and you can play them, and it reflects them, and so on. So that's great. So try another. Okay. Oh, it gave us one. No, let's not do something so crazy. Okay. You want to do benzene? We know some of the symmetry elements of benzene, but we haven't done the point group of benzene. Is it linear? If you said yes, I would tell you to leave. Okay. Does it have a no? Okay. Does it contain 2 or more unique C3s? No, yeah, there's some 3-fold and 6-fold symmetry in this molecule, but it doesn't contain 2 or more of them, right? So we'll say no to that. Select the highest order. So what fraction of a turn would leave the molecule unchanged? A 6th, yes. Okay, so we come over here, we pick 6 and select. Okay, so we've selected it. Now I'm going to put that up and down. Okay. So now the principal symmetry axis is the z-axis. It's the vertical axis. And so then we want to, we've selected it. Are there 6 C2 axes perpendicular to the highest order axis? So this is the vertical principal symmetry axis. The C2 would have to be this way. And look, we're looking at one, aren't we? If I rotated the molecule halfway over, the hydrogens on the left would be on the right. And the carbons on the left would be on the right. So yes, the hydrogen-carbon axis or bond is a C2 axis. Okay, and so every one of those is a C2. Well, that gets us 3 C2s, right? I could have one this way. I could have one this way over here, connecting this back hydrogen to this one, and I could have one this way, connecting that back hydrogen to this one. So that's 3 C2s. But I also could go this way right here between the bonds. Can you see that that's also a C2? So in between all the bonds, there's C2. So I've got, now this one's number 4, and there's another one over here, number 5, and another one over here, number 6. So there's 6 perpendicular C2s. And typically if you find one, it's got 6-fold symmetry, so you just rotate it 1/6 of a turn, and you're going to see all of them. So this is 1. I rotate it 1/6 of a turn. There's 2. There's 3. There's 4. There's 5. There's 6. So that's that. So I would say yes. Now that puts us over into the D groups, over on the far right. So there's only 3 options now. Does this molecule contain a horizontal reflection plane? So this is now the vertical axis. There's a reflection plane that's horizontal. Yes, it's a planar molecule. So just every planar molecule has a reflection plane. This is just asking, is that reflection plane the horizontal plane? And it is. So the C6 axis is going up and down. The plane of the molecule is a horizontal plane. And so I say yes. And so that's what that H stands for in D6H. A D6H molecule is a molecule with 6-fold symmetry that has that horizontal plane of reflection. Okay, let's check our answers. Yay. Of course we got it. Okay. And so we can, here's, show, we have the principal symmetry axis. You know, we can play some of those rotations. Here's the C2s, the 6 C2s. And we can play one of those. So there's the C2 rotation. And here's the horizontal reflection plane. So if we play that one, we won't see anything because it's at the top of the ball, right, reflecting into the bottom of the ball. Okay. So that's pretty fun, isn't it? This is better than Sudoku. I mean, a long shot. Yeah. So if you like games and things, maybe this is your part of the course. You know, so that's great. So let's. We're coming up on time. Let's do one where we get something wrong. Okay. Yes. It has to. Notice all of these symmetry elements contains the center of mass. So the axes are all going to go through that center point. And it has an inversion center. Notice we didn't get into the question of an inversion center in doing the flow chart for this particular molecule. There are occasionally some questions about inversion centers, but we're not, in order to get to the end point on the flow chart and identify the Schoenflies notation, we don't have to identify every symmetry element. Those are in the character tables. So once we find D6H, we go to the character tables and we see all of the others. And you'll see reflection planes and things that you didn't necessarily see in completing the flow chart. So practice with the flow chart. You're going to practice also in the lab. You can build your molecules and learn how to draw them. And then Friday we'll play around some more. We'll get into the character tables. All right.